our final speaker today is Charlotte Voght. She's a PI at the Technion Israel Institute for Technology, where her group focuses on using spectroscopy to gain fundamental understanding of the catalytic processes that will fuel the future. Things like carbon dioxide valorization, fuel cell technology, nitrogen fixation and utilization, hydrogen production, and the recycling of plastic and other waste. So just a few little things here and there. Voght earned a PhD from Eindhoven University of Technology and Utrecht University, and has also done graduate work in management and business, which is, I mentioned, because she's currently commercializing one of her technologies in carbon capture and sequestration. Cheryl, thank you.
Thank you very much. Let me just grab the pointer over there. Thank you. Oops. So first off, I'd also like to thank the C&EN committee for this great honor. That's really amazing to be under such a group of inspiring people. And I'd also like to thank you guys for being here, as I'm the final speaker of the group. So I'm going to circle back essentially to what Paul was telling us this morning. On the one hand, that you have to be a little bit crazy, and on the other hand, this sort of reductionist approach and closing the gap between constructing something with it, right? And that's what we essentially focus on. A little bit about my background. So I am Dutch. I was born in the Netherlands. And for those of you who don't know that, in Northern Europe, Germany, the Netherlands, Denmark, also Belgium, there's a relatively strong history of chemical industry. And despite that, when I told my friends that I was going to study chemistry, all of them asked, what are you going to be with that? Do you want to be a chemistry teacher? And so this decision to go into chemistry, I'm pretty sure I would not have made had I not had a really good example, which is my father. And I know that I'm very privileged to have that example. He worked in the chemical industry his entire career. And sort of showed me, he's a very enthusiastic explainer, showed me how amazing the world of chemistry is, and got me eventually into choosing that. So I know that I'm very privileged in that sense. It also got me to Utrecht University, where Bert Werkhuizen is. He is one of the main people working in the field of operator spectroscopy, and I'll explain in detail what that is in the next couple of slides. But I've had extremely strong mentors in my career that I really have to thank for where I am today. Bert Werkhuizen, I also want to mention, one of the greatest things about him is that he is one of those people who, instead of saying, that's never going to happen, or this can't work, he's the person who says, let's just try. And he was also one of the people that I felt comfortable in, poking his questions, his even though he's not Dutch. The Dutch are very non-authoritative, and they speak to each other very directly, and they're not so afraid to question the status quo. This is what he really allowed me to do. He gave me a beautiful support to do all of these things. And I moved to a country in the meantime, Israel, which is another one of those countries where you have sort of ingrained in the culture to question the status quo. Why are we doing it like this? Should we be doing it like this? Can't we do it this way? My mother always said, I hope that you get a daughter like yourself so that you know what it's like. And I am lucky to have a group of amazing students who are like that, who question everything I tell them, which is exactly what they should be doing. And so after my move to Israel, where I'm also gratefully enough involved in setting up a new catalysis center, a new center focused on really bringing some of the brightest minds to Israel to bring clean tech to fruition fast. I set up my laboratory in spectroscopy of catalysis about 2 years ago, and we try to answer really fundamental questions. So catalysis, I'm sure most of you know, is involved in at least a third of the world's gross domestic product. It is going to play a key role, I believe, in the energy transition. And then I always think of the French teacher that I had growing up who said French is the most important subject that you'll ever have, in high school. And I still haven't figured out why that is the case. And this is what I'm now also saying, right? Catalysis is that thing which is going to allow us to transition faster from a fossil fuel dependent world. But I do really think that that's the case with catalysis. And yet most of the catalysts that we develop by trial and error. There's very little rational design, or very little successful rational design. They're extremely complex materials. And what do? We go for the reductionist approach. So we've tried to understand them in terms of simplifying systems by taking a single crystal facet, or a static approximation of what kinetics looks like, right? And the more that we think about these, or the more that we're actually able to do with also modern day tools and modern day computational chemistry, the more we understand that picture is far more complex. And in order to design the new catalysts, the new materials that we need to close the gap of where we need to be technology-wise and where we are right now, as fast as we can, we need to propel the way that we need to change the way that we're looking at these types of systems is our thinking. So that's what we do. We try to look at fundamental questions by studying catalysts at work. And we also, on the other hand, because as was mentioned, I also have a degree in business, we also try to look at these problems with socio-techno-economical analysis. So I always like to understand what type of an impact the things that we're studying in the laboratory can actually have. And then sort of choose the thing that I think would matter the most. So since 2 years, we've also had big issues in building our laboratory and attracting students. But we have a wonderful group now, as I said. So the premise that I want to talk about today is, starts out a little bit bleak, and that is that if we look at the energy technology deployment laws that have existed since as far as we have been, deploying these things on a really large scale, we know that we can, irrespective of if it's fossil fuel based, or if it's nuclear, or if it's renewables, we can grow a technology up until a certain level of materiality, and that is approximately 1% of the global supply in energy. That's not a lot. And then afterwards, we grow linearly. So exponential up until only then, and then it's linear. And that has really big implications for how fast we can decarbonize and how fast we can employ specific technologies. It means, for example, that, we've heard it today earlier already, the 1.5 degree global temperature increase. How likely is it that we can reach that? Not. Yeah, it's not likely. Really not likely, actually. This is the energy supply and demand up until 2050 if we follow that premise, if we follow the 1.5 degree global temperature increase. And two things here need to stand out. One is that we are not allowed to increase our energy consumption up until 2050. Not going to happen. And secondly, we have to start growing our renewable share exponentially from now on. And we also know that's not going to happen, right? So the way that we need to start looking at carbon dioxide removal technologies, for example, I would argue is twofold. On the one hand, we have to, as fast as we can, employ things that are at a really high technological readiness level. And I'll talk about some examples now in this talk. And on the other hand, we have to keep in mind the big picture when we're choosing to invest in new technologies in such a scale, right? So the scalability in order to employ systems on a really large scale to actually make an impact is not as easy as we sometimes look at it. DAC, for example, direct air capture, if we just look at the sort of thermodynamic bounds in which we operate with DAC in a Carnot cycle, right? A heat swing, energy efficiency losses, etc. In this sort of best of best case, we're going to be using 1/3 of the world's energy supply by 2100 if we are removing the carbon dioxide that we need to remove with DAC. Yeah? We need to come up with something better. And so I said the talk today is going to be more about the sort of intermediate part, the thermocatalysis technology that we're, that's drop-in that we can deploy tomorrow. And it's sort of under this frame of thought. We are in time moving towards trying to reach this 1.5 degree global temperature increase. We have two options, essentially. One is we can rely completely on some technological breakthrough that will happen tomorrow and then hope that that's going to steer us right into a sustainable world. And the other one is that we can understand that we can do things organizationally. We can have things like carbon credits. We can have these incentives to work with more carbon neutral technologies, and that will end up in a scenario, in a much more likely scenario, if you ask me, which is much more reliant on waste and also a little bit of solar, but still also some fossil fuels. That means that a lot of the processes that we have steel in the ground for today, billions of dollars of steel in the ground, are going to be around for a while, and that acknowledges that. And so we're going to have really high concentration point sources of CO2 for the coming years. And one of the things that you can do with that is use that as a very big battery. So you can use point sources of CO2 together with hydrogen from electrolysis to store energy, green energy, electron surplus in renewable electricity in chemicals, right? And then burn those and then keep that in sort of closed loop. And the question that we ask ourselves is, how can we make such processes, thermocatalysis in general, I have to say, but we were focusing on this one specifically because CO2 is also nice to see spectroscopically. And so which handles can we turn to make these reactions much better? And we turn to spectroscopy, use, for example, X-ray absorption spectroscopy at synchrotrons, also at SLAC, where we use high-energy photons to knock out a core electron of an average absorbing atom, and then see how that thing moves around, and use that in order to assign some physical properties of our catalysts. Problem is that such techniques, here you see one in a CO2 environment, and you can see one in a hydrogen environment, and you can really tell the difference, right? This is the difference spectrum, and knowing that X-ray absorption spectroscopy, typically you have about 10%, if you're in a really good system, about 10% error bar that you're working with, maybe 20, 30, some would argue. And for vibrational spectroscopy, it's not much different, right? In order to understand the systems and how they're working, we have to be able to deconvolute which of these species are now actually active and which are not, in order to rationally design that we have more of the sites which actually are active. But how do we differentiate between those in such a system? You can see all kinds of different signals coming from all kinds of different adsorbates. And so this is sort of the problem that we're working with. We have a very small fraction of active surface sites, right? And of that fraction, there's a very large variety. And that large variety, only a specific amount or a specific type is really active. And that adsorbate surface system changes dynamically, and we want to try to characterize that spectroscopically. And that's also why we've been simplifying these things for such a long time. So in my PhD, and currently we're developing this technique in all kinds of other applications, we've developed a sort of general experimental toolbox where we apply pulses to our system, something that is catalytically relevant, right? And we try to identify those minority species that are actually doing something. And we do that, I won't go into the actual physics of this, but we do that by essentially trying to assign the highest variance explained in a very large data set using PSD or using singular value decomposition principal component analysis. I don't have too much time, and I don't want to bore you, but just an example of what we were able to do in such a system. This is if you take the traditional approaches of trying to study such systems, these are the type of signals that you work with. No wonder that so long we were not able to identify these tiny species. If you then employ that general methodology, we end up, for the first time, we were able to look at changes in a catalyst system that correspond to less than 1% using a technique that typically, you're at the 10, 20% error bar. And we were able to explain exactly why this reaction, CO2 hydrogenation over nickel, a thermocatalytic reaction, behaves the way that it does. And then we can use that information to tune the activity of those active sites to make the types of products that we want. And so eventually we know, or we summarized all of these findings into sort of this geometric electronic and confinement contributions on the active site. And for these catalyst metal nanoparticles, we did a really extensive study on how CO2 absorbs on the surface, why, what types of reaction pathways you can take. And like I said, we were able to increase the selectivity of this reaction. Again, also model reaction because we wanted to study these spectroscopically, but still some very interesting results have been attained where we can increase the activity of carbon-carbon coupling over such catalysts by over an order of magnitude by tuning the support. And I'm not showing today because I realize that this is also something that's going to be broadcasted, but just a little bit about it also because it was introduced, right? Having these types of knowledge, knowing how we can tune the activity of the active site, knowing the big picture where we're standing, that we need to develop carbon dioxide technologies which are much more energy efficient. We're now developing a technology, and it's also very much came to fruition, or came to existence because I live in a country where these types of technologies are applied. Desalination technologies, for example. This brought me into a whole different field of looking at the world, coming from my chemical industry background, and combining those fields of knowledge. I think it's been said a couple of times, right? We're not going to be able to solve all of these challenges by ourselves. We need to cooperate, collaborate, and really look through different fields and sort of merge everything together. We now came with a technology which is going to be, if we apply it on the largest scale and are talking about hundreds of gigatons of CO2 removal, we're talking about, in the single digits, if not even lower percentages of energy supply in terms of carbon dioxide removal. So hopefully ending on a slightly more positive note. And with that, I would like to thank, my amazing group, and I'm very lucky to work with my mentors, the people that I've collaborated with worldwide, been lucky enough to travel around like this, and also definitely the funding agencies that are allowing us to do this cool science. So if there are any questions, I'd gladly take them. I also fully understand if people want to go to lunch.
That was a great talk. Thank you very much, Charlotte. I just have one question. If you were to guess what the future of operando is going to look like, what would that guess be? Or if I could put it a different way, if you had a little dream or some kind of fantasy about some kind of unbelievably amazing operando technique that has not yet been tried out, what would that be like?
I think it would depend who you're asking. If you're asking me, so we have this dream in operando, and it's something that Bert always puts forward. I would say it's the thing that I grew up with, right? Of this molecular camera, this molecular video camera, and he's been doing beautiful things in spatial resolution. Very important because we always assume that our catalysts are completely homogeneous when they're heterogeneous catalysts, right? And they're local, even intraparticular differences in gradient of reactants, etc. So that's on the one hand, which I'm not focusing on. We're focusing on high time resolution, so the other part of the camera, essentially. I think that the most exciting thing in the field of catalysis right now is that we're slowly recognizing that looking at our system statically is not going to. We're going to stay within the sort of thermodynamic bounds that we're operating in and have been operating in for the last 100 years. If we are able to describe our systems dynamically and seeing how dynamics change, perhaps we can get from 10 to the power 3 for the best industrially applied heterogeneous catalysts to more towards where enzymes are operating, where there's really, really orders of magnitude difference. And I think that the biggest, it can't be really anything else. The biggest difference between those things is the different time scales at which they vibrate. It depends on which enzyme, of course, but milliseconds to femtoseconds, and on different areas within that catalyst. Within those, nature's fully optimized catalysts, they have different frequencies of vibration which allow the active site to just be much more active. So we need to do that.
Bravo.
Thank you.
Brilliant talk. You also win the prize for best slides that I've seen this whole meeting. That was, I have to find out how you made some of those things
I'll
happen.
be happy to explain.
Yeah, so I just wanted to say I didn't find your talk pessimistic at all. I found it very hopeful. We're working in similar areas of catalysis for CO2 conversion. And I guess my question when I step back is, when we look at how we make this transition, make progress happen, the things that are available today, like immediately, not in the future, we know that even as simple, almost non-technological, where if we ended natural gas flaring, that's about equivalent to 40% of what the EU uses in natural gas, right? So that alone. The technology of CO2 conversion, even to simple alcohols, methanol, ethanol, or simple kerosene, paraffins, just if that were implemented at scale, that gets us to somewhere about between 10.5% and 11% of the CO2 targets that we need to get. So there's things that are available right away. I am in complete agreement with you that catalysis is going to be critical, essential, necessary. You can decide whether or not this is a real question or a metaphorical question or a rhetorical question, I should say. You talked about catalysis design, right? And how we need to rethink catalysis design and how it needs to be coupling systems with reductionist approaches. Now I want you to think about catalyzing the implementation, okay? So using catalyst design as metaphorical catalysts. How do we speed up the transformations that we're going to need?
I have to assume first that we know how to design catalysts, which I'm not too sure that we're able to do. But you're very correct in saying, right? We have these laws that we've apparently adhered to over the past couple of decades. Right, and there are also clear ways, there are reasons, understanding, let's say, the reasons of why those things behave the way that they do, right? A big one of them is amortization. I only read the word in general, so if I'm not pronouncing that correctly, then sorry. But, right, we have approximately sort of 4% of the overall energy technology, the CapEx energy technology, goes out of use, right, per year, and therefore that chunk of it can be renewed, meaning as much as if you want to speed up that process, you have to have something that is better than what is currently being done, because that's the only, I think, is still, we can't break economy, we can't break the way that the economy works, so if we want to break that sort of linear trend of adoption or deployment, then we have to have something that is and cheaper and better, right? Because otherwise we're going to simply only renew, we're only going to we're only going to invest the CapEx into something that, that needs to go off of the supply. So, you can think of things like having smaller reactors in series, right? So that you can have a faster renewal of those technologies. So I think that this is one of the bigger things that we should also start to employ. So having mini reactors instead of having these billions of dollars of steel in the ground is going to really help us to renew technologies in a faster and cheaper way. So does that answer the question at all?
I'd say yes.
Okay.
And we know that unit process optimization is different from system optimization.
Yep.
But it's a longer conversation. Thank you.
Right.